Welcome to the seminar. We'll be talking about signed distance functions, and we will spend most of the time just coding them. We will ignore applying any materials on the geometry that we make, and we'll also ignore how to render it, because there's tons of information that you can find on those topics, and making the geometry is interesting enough to fill 3 hours or something, and we'll have enough to do anyway. So the thing is, you might have seen probably on ShaderToy or some 64K or 4K intros that use this technique to make scenes and to make some content. It's usually people call it ray marching. This is one of the ways to render those distance functions, and I'll just start by looking at a video. This is a demo that we made. I'm not showing the whole demo because it's 7 minutes long, so I'll just be skipping through it to show you some impressions of what we've done with this technique. So this is our 64 kilobyte intro. It's called The Timeless. Was from last year, and yeah, that's what's in it. And everything that you see here is made with those signed distance functions. And yeah, in this talk, I hope to show you how to do it. So we'll go back to the code. So basically, a signed distance function is this. This is a function. It returns a distance, and its input is a point in 3 space, so x, y, z. And yeah, what it returns is, in this case, the distance from the origin, the length of p, minus 1. So at those values that are on the sphere with radius 1 from the center have exactly the value 0 in this function, and by definition, 0, that 0 point cloud, that shell is our geometry boundary. So, and right here we see the output. It is a sphere. So, and if I just, for example, change this number, yeah, I will get a smaller sphere. So basically, the thing is, you sit down, you want to write a function that returns this kind of distance. For a sphere, you can do it. And probably, if you take some paper, you can do it for a box as well, for example. And the problem is, how would you do it for a more complex thing, like this city scene? You just can't sit down and write it on paper what the distance to a mass of buildings is. So you need some approach how to break it down to. You need some patterns how to create more complicated content. And yeah, the goal of this talk is to show you some of those patterns that we found that help us to make this kind of content in a somewhat structured way. So you have some goal in mind, and you can try to go there. And try to achieve this thing that you have in mind. So we'll just start with more examples. All right?
Can you enlarge the font size, because the people say it's not readable on the
All right. Is this better for the stream? Yeah. So can someone on IRC or so? Okay, thanks. All right. So I will use this. For many primitive objects, we have made functions. I will use them now. I'll show the code for them as well. So this makes a box. You can see on the floor, there's those lines. They show the distance to the surface, so we can get a visualization of the distance field here. The implementation of this, I have this in another file, some library-like thing is this one. It's really not big. You don't really get it by just looking at it for a few seconds, but if you sit down, I'm sure it's not a problem. Also, you can find information on all those primitive objects on Shadutoy or on the ray marching toolbox thread on Poet. So there's tons of information on the primitive objects, and I'll just use them, and we won't go into the detail on that. So, yeah. So we have a box. All right. So we'll try to do something a bit more interesting now. So I'll make a cylinder. Ignore the box for now, look at the cylinder. So you see, yeah, well, not very surprising. For the cylinder, we can just scroll down to wherever it is. Yeah, there's a capsule, there's a cone, there's a cylinder. So very small function, not really that interesting. You can always try and make that if you want. So first thing is, I'll just flip the coordinates for that, and then we'll try to display both the cylinder and the box. So we do it this way. So I've just written this. We take the minimum of the cylinder and the box. That means we take the smallest of the distances to both those objects. That means we ignore the object that is further away. So we only take the one that is nearer to the point P that we are evaluating at the moment. And so we get the union of those objects. So we've used something like a Boolean operator. If we use the maximum, it's the opposite. We get the intersection of those. All right. So far, you can still, well, it's not that interesting. Now we have made some additional operators. For example, this combine operator. And if I look at the point where the objects meet, we see that there's now a smooth curve. And the idea behind this operator is many objects intersect at right angles. So both distances to the distance to the cylinder and the distance to the box, can be interpreted as two coordinates of a coordinate system. So I'll just go there. Where is it? There it is. So it's a bit more complicated. I don't want to go into detail again, but the basic idea is we build a local coordinate system from the two distances, and in that 2D coordinate system we write a quarter of a circle, and so we get this intersection, and we get this smooth curve from one object to the other. And if you look at the distance right here, you see that the lines all have the same distance from each other. So it's still a perfectly good distance function, and many other smooth minimum operators don't have that. So the mathematicians call it the Lipschitz constant. It's the rate of change when you move in this distance field, it's still 1. So if you go from one point towards the surface, the distance function changes by exactly 1. So it's still a good distance function. So in this local coordinate system, you can do things as you want. In this case, draw, for example, this 45-degree plane and get this this kind of thing. Then I'll move this cylinder a little bit. Well. So the cylinder now gets evaluated like this, and we can, yeah. This kind of thing is nice to make more technical looking objects, or maybe for architecture or something, and it doesn't look that organic. There's another one I made, I'll just show you. This one takes another parameter, and what this one does is just make those, well, whatever you would like to call it, but that's a useful thing, because it looks like there's actual real complicated geometry, and when you think about 3D modeling something like this, you have to take care of the corner, all the vertices have to fit together, and it's real, yeah, it's a real issue to create something like that. And if you just write this very, very little piece of code, you can always change everything at all times. So maybe at the last minute you decide it looks better like this with 4 instead of 3 of those column things. So you can always do that. I'll show you the intersect operator of this flavor as well. Looks like this. So we get the intersection of those objects. And if I move this ground plane, we can look at the distances here, and the distance field still looks all right. There's a few edges right here, but well, all in all, it's still good. So the message basically is, if you combine objects, you can always try to use this to create additional content at the intersection, which might be more interesting and more complex than the two objects themselves. And this really helps to create rich scenes with rich content. All right. I'll go back to the boring minimum. So we again have this thing. The second thing that you need to create content is have more than one instance of an object. And you usually do this when defining distance functions by applying the modulus operation on the domain, that means on the space. So I'll just show you. Let's make it 20. So often it just looks like this. Oh, well, wrong. All right, so what's happening? The object at the beginning was centered on the origin. Then we add a value, for example, 10. So what was before 0 is now 10. Then we take the modulus. It's a very cheap operation. Just comes with a graphics card. Basically, one instruction. So 10 stays at 10. Then we subtract 10. So in that case, nothing happens. For every value that is more than 20, say 30, will end up at 10 as well. So at 30, we will have the same result for the rest of our computation as at 10. So for really not much cost, we have now many of those objects. And yeah, we'll try to do something interesting with it. So first, I'll change which axis we use for that, because I have something in mind. Then we'll increase the thickness of the box for a bit, and also, well, let's increase the radius of the cylinder. All right, so now we have this tombstone-like object, and so now we'll do some things with. The interesting thing is, I almost forgot, this thing, you're doing it so often that it becomes tedious and distracting, because there's 3 numbers, but basically it's just one number, this one, and the other, well, if you want to change anything, you have to touch all 3 of them. So you can just make this a function. I call it p mod 1. That means it's an operation. It's just shorthand for this operates on the space. Does a modulus, and it does it in 1 dimension. So all right, so nothing happens. This is good. And if I now want to increase the distance, I just change 1 value and everything works. So this is an operation that changes that value in place. That looks a bit counterintuitive if you don't know what you're doing, because that might not be the first idea, but it makes sense because you can optionally use the return value, which is an index to the cell that you're in. So our original object will have a 0, the one on the left side will have a -1, on the right side will have a +1, and so on. So you can use the cell index to introduce some variation, like using it as a random seed, and use that to introduce differences between those objects. So look at the implementation again. I think it was there. Yeah, so looks like this. Basically the same what we've just written, and it except that it also computes this this cell index. And I've many more of those operators, and yeah, well, you can always invent more, and it just makes sense to encapsulate all of those space repeating operations into some kind of function, because you'll need them again anyway. In this case, you can just keep the code a bit smaller, and so this way you're just writing exactly what's going on. You say repeat every 20 units, make this, and use them both. So it's very semantically dense, the code that you get if you don't write the modulus operation explicitly. So what we're now going to do, we'll call what we have just displayed, those objects we'll call a window. And we will make another object that we'll call a wall. So I'm using another flavor of the box function. This one is one that is only defined in 2 dimensions, so it's an endless box basically, almost the same as the one that we've just seen. I wanted to extend endlessly in the z direction, so I'll put x and the y, and it will have a width of 1 and a height of, well, let's say 15. And we will return, let's just start with returning both the window and the wall. So now we have this. So you probably see what's going to happen. I have this divide thing, which is almost the same as the intersection, but I'll use this flavor, for example, and it only that it's that the second object is inverted. That means for the second object, if you just flip the sign, oops, read like this. If we flip the sign of a sign distance function, we get exactly the opposite in space. It means just the outside of the object. So we intersect, I mix it up here, the wall with everything that is not a window, and that means we cut it. So now we have this cutout of the wall with this nice chamfer thing here. I'll use this one again, make it a little bit bigger, and use 3 of those columns. And all right, so probably can be. All right, so all right, not bad still for the small amount of code, but that doesn't really look like anything you'd see in architecture so far. And we'll try to fix this. So by manipulating space a bit more. So this is a mirroring of the one of the axes of space. If I do this, absolutely nothing happens because the object was symmetric to begin with. But what if I subtract 2 in here? All right, what happens? All right, I have to do this afterwards, of course. So we get this. All right, this looks better already. And yeah, well, let's just do something like this again. All right, so now we have this paired window things. This column down here starts to look like something that we actually might find at some church or something. Cool, all right. So we've made a wall. I'll have to check the time. All right. So now we want to make a building thing out of this wall. First, we'll need a roof. So we'll probably, I'll do this here. Or actually doesn't matter where we do it. So now the code becomes a little bit dirty. I could do this better, but I won't for now. The height of our wall is 15. We've moved 9 already, so we'll move another 6. So now our origin is at the very top of the wall, and then we'll just put a box there to make a very primitive roof. So the roof should be an endless one as well. So it we'll ignore the z-axis again, and it should be should have some extent in x and should not be that thick. I will just do it like this. By the way, if you have any questions or you notice any errors that I'm making, please don't hesitate to just interrupt and ask. I'm really open for that. All right. So very ugly roof. Have to move it to the side a bit and make it. Maybe it's a bit too thick. So, all right, still way too flat. So we'll have to rotate it. So we get a new operator thing. Maybe I should have named this PR, but we're too used to it now, so it's called this way. This rotates. This manipulates the P, so the new coordinate system is rotated around an axis. So it's rotated around one of the principal coordinate axes. And I specify that by the two values that are manipulated. So I'll turn it around the z-axis by whatever 0.7. See what happens. I'll show the code later. All right. Okay. I see I've probably done something wrong. All right. Mixed up the sequence of the operation. All right, so now it's more what I wanted. So it's basically the process is always the same. If you're using operators or not, you're just manipulating space in a recursive fashion, like a bit with like a scene graph that you might be used to, like stacking operations inside each other and manipulating it this way. It might seem that everything is a bit reversed. So the intuition is often I want to increase the y coordinate of my object. Why do I have to subtract something to make this happen? The reason is you don't move the object, you move the space around the object. So in order to move the object to the top, you have to move space to the bottom. But once you get used to it, it becomes a very natural way of thinking. So still, our building is not that interesting. I'll just make some very slight adjustments so it looks a little bit better. Okay. So now we start with the interesting part. We will mirror space once more to make the other side of the building, to make some kind of very, very endlessly long building thing. So again, if we do this without moving anything, wait, this is the x-axis. So now this was more or less the opposite of what we wanted. So yeah, then let's add this minus sign to make it right again. And yeah, I'm mixing up the signs as well, as you see. Okay, this is starting to go into the right direction. So with this number, we can now control the width of the object, and I can just put this on a value that I can control with the tool right here. So in principle, this is something that you can animate now. So this is really good for designing things, like mapping those values to some sliders and tweaking them until they just look right. Okay. Still not very interesting. We'll use another operation. Look at the implementation in the moment. Let's try it like this. Okay. Now it approaches to look like some building thing. So what did just happen? Basically, this operation takes the absolute value of those two coordinate axes again, offsets everything by 40 in x direction and 60 in z direction, and then if x is bigger than z, switches between the two, which basically is mirroring at the diagonal. So, and we see that this is exactly what's happening here. Locally, I don't know if you can see the mouse cursor, but there is this mirroring axis right here down the diagonal value. So, yeah, but we don't have to stop here. We can do more. We can just do this again. Let's just do it with 90 and whatever. So now we get this. So now at this point, I couldn't really have predicted how exactly it would have looked, what we get. And well, one way is just to, well, try it out. But of course, you can always plug in some values and just play with them to see what's happening. So now when you play with it, you can intuitively get what is happening. So you see the mirroring axis where the building intersects, and yeah. So this is now approaching to look like some sort of interesting right now. So you could always add more detail, and still, if you, for example, you still don't like how those window things look, we can always go back there and increase the size of one of those. Okay, it looks better. Maybe increase it even to 1. All right. Maybe now we're satisfied. So you could now add some columns in the interior, for example, if you wanted, or add some more detail on the outside. And with this space folding thing, the good property is the distance field, as you can see it on the floor in the visualization, is still good. So I can just go in there, look at the details. Everything looks fine. This distance lines, they are the black lines are always distances that have the same value. So it's like height maps on like height lines on a map, and it's still consistent. There's no discontinuities between them, because we've just used a good distance field in the beginning and then mirrored it. So the invariant is the distance field is still good, and we didn't cheat by bending parts of it or something. So when you look on ShadowToy, for example, many people add detail by warping space, by adding noise or adding sine waves or something. And this always makes the distance function to be no longer correct. And that makes all kinds of problems. And I strongly suggest to always only use distance functions that are really distance functions. So, or to be more precise, that are distance bounds. So, for example, you see here, the lines don't form quarter circles as they should, because the distance from this corner should normally be circular. So the distance function has a bigger estimation. So it's correct right here at the top, but in the corner it's off by a factor of the square root of 2. But it's off in the way that it estimates less distance, so it's still safe for rendering it. So, for example, if I have this visualization, you might render this scenes like this with sphere tracing, which basically means you start at some point, sample the distance function, walk along your view ray, exactly that distance that you just got, because you're inside a sphere that is safe. And then at that point, you sample it again. And so you see the first circle doesn't touch the geometry. That's because we estimated too much, which is okay. We just lost maybe 20% that we could have worked a bit further. But the second one is touches the geometry again. So, by the way, in case you're wondering about the rendering method, this is the original paper by Johann, who invented this way of directly rendering those distance functions, called it sphere tracing. It's still a good read, still a good paper. There's also more recent papers like this one, which show some improvements on the method, and tons of tricks on shader toy. So concerning the rendering, you can always find more resources on that. Okay, so this technique right here is basically how we made the cathedral scene in the Timeless. I don't know if you've seen the actual intro. I can just here, this one. This is exactly it's very dark, I guess. I'll try to find a more colorful part here. This is exactly the technique that I just showed. So it's just with more detail, and it is more than one level, and there's columns in there, and the windows are colorful and whatever, and the space is folded in a maybe a bit more complicated way, but basically it's exactly what I just showed. And okay, so I'll just switch to another scene that I've prepared to show. All right. I will show one more operator before we do that. I'll just use it right here. You can. So far we've only repeated space in along coordinate axis, but you could also repeat it like in an angular way. You'll see in a minute what I mean by that. So I think we have one more free variable here, so we'll just use that. I have no idea what it's actually set to at the moment. All right, so this is what just happened. If I set it to 1, nothing happens. This is what we started with. The values in between the integers are, well, in this case, the output is okay. But generally, if you, like, for example, set it to 3, you see that one segment stays the same, that is not affected, and the others are, copies of that. So, you can increase this and whatever, make interesting shapes. So now it almost looks like a intake of an airplane or something, or maybe on the inside you will make some really big hall with interesting ceiling, and we've made it just like that, just by experimenting, just by holding space. And that's really quite often the way it goes. So we can, for example, tweak it like until those column things almost disappear. So yeah, maybe this is interesting. Maybe this is what you're looking for. I don't know. So, and again, the implementation for this is really simple. You take you compute angle from those two coordinates, so convert it to circular coordinates. Then you apply the modulus operation on the angle. Then you convert it back to Cartesian coordinates, and then you just continue your evaluation of the distance function as before. So let's look at the completely different scene now. I've modified it already. So we don't have to look at all the code because it's old and very, very messy anyway. So this is an object that is made using all those techniques that I just showed. So the basic object, one of those gears, is just one function, and it's made of two cylinders that are combined with one of the operators to make this chamfered bevel thing. The parts that stick out, the cogs, are made in the same way and then repeated and mirrored with the angular repeat operation, and then the whole thing is stuck together and repeated in an angular way again. So I think this is probably animated. Yes, it is. So you can, if you watch closely, you can see that this is actually a Möbius strip of interlocking gears, and I recommend against implementing things like this because it really melts your brain, and it's actually 7.5 repetitions around the middle, because you get 1/2 less repetition because the thing is twisted in itself. So, but basically, we've seen everything that we need to make this. I've shown everything that we need to make something like this. So you could basically sit down and, do it. An interesting optimization is at the very beginning of the gear function that computes the gear, I've made this object. I've called it H for whatever reason. And if I just return this and disregard all the things that come down there, I get this very thick rings. And if the distance of P towards this very cheap object, this very cheap bounding object, is bigger than some value, I return just the bounding object. That means I skip all the calculation inside. So one big speed issue normally is that you have to evaluate for every point in space all the other objects, but maybe you're very far away from them. So I might be evaluating maybe imagine this object is set inside on a pedestal inside a building or something. When I'm very near a column of the building, I'm evaluating the distance toward one of the gears, which is totally unnecessary. So often you can just skip that by having, I just call them proxy objects that surround other objects. And for example, this one there could be a cylinder around the whole object, and to just skip the calculations if we are for example, near the ground plane and very far away from the gear thing. So you can nest those proxy objects, and that really saves enormous amount of time. All right. Generally, the best advice I can generally give you when you're crafting distance functions by hand is don't use loops. Don't use a for loop ever, because anything can be achieved by repeating space. Often, when I look at when people are new to this, they say, "Oh, I want 5 of those," and then they write a for loop and evaluate 5 of them, use the minimum, and it works. But it's 5 times more computation that you would need, and you should just always use repeating space, and preferably with some operator thing. So, for example, I've made an operator to repeat an interval of objects. So it works exactly like the 1D repeating thing that we've just seen before, that we used to repeat the windows, and you just give it two additional values for the first and the last cell index, and so you say start by -2 and at +2, and it will give you 5 of those objects. Okay, I promised you to show you more, so we'll just switch to the city. So now we're stuck inside a building. All right. So this is the city scene that you might have seen in the intro. If you look at the floor, at the distances, you can see that there are discontinuities. Like here, it doesn't really match, but it's not that far off. And sometimes there's some artifacts due to those discontinuities. So you can see one here, but you could either choose your values carefully or just look the other way where there's no artifacts, which is what we mostly did. So I'll just show you the thing from another perspective to make it a little bit more clear what's going on. First thing is the buildings all look a little bit different. Some of them have those terraces, the roofs are different, some have spiky things. They all have very similar style, but there's little differences, and that makes the scene a lot more believable. So I'll just deconstruct this a little bit. I don't think we have that much time. Oh, no, we don't. So this is a lot of code, and it's very old, and it was made in a very, very short time. So really don't have to look at everything. But I'll just comment out random stuff, and we'll see what happens. So you can see that I just used many of those operators there. So now what happens? Right, why is this wrong? So now what do we see? Okay, everything's a bit broken, but what you can see is I've removed some of the space folding things, and now everything has become one big facade, and which just changes its appearance once in a while. So we've used some index to change appearances, but in the end, the whole city is just one big facade, which is exactly the same thing that you've seen at the very start when we've made this building with the windows. it started out as an endless facade as well. So you just have to wrap it in a certain way to make it into buildings, and then use the indices of this space folding to introduce some variation. Can't go into the detail, but in the end you see it's just a facade, just one, and there's those columns, and of course it's only one column because space is repeated again, and so the whole city is one column, one window, one floor plane, one street light, and this is all just mirrored and repeated, and then shown with the right camera angles, and that's basically it.